My name is Jonas Sadak, and I'm going to talk today about the security of embedded firmware. And we did a large-scale study for this that I'm going to present here. So who is we? First there is André Costin, my colleague, and me, who did most of the programming work, and then our supervisors, Aurélien Francillon and Davide Balzarotti, who were also in the design of the system involved. So we come from Euricom. This is a private research institute in the south of France. It's also a graduate school for master students and PhD students. And we're around 30 professors, I think, and 50 PhD students. Okay, enough self-promotion. So why are we here? So first, why is firmware interesting and why the security of firmware? Well, nowadays you have systems running code a bit everywhere. Trains are running completely autonomously, car, planes, ships are steered by wire. Then power plants and factories are running on microcontrollers, and so on and so on. So you see that there are plenty of embedded systems out there. But the point of those embedded systems is that on their own they can do some things, but they cannot do that much. They really get smart if you connect them. So if you expose their data and their configuration interfaces and control interfaces over a network, then they can talk to each other and they can coordinate. But then they can get really smart if you connect them to the internet. And when you connect those devices to the internet, then of course you need to rethink the design, because devices that were conceived before for safety and security critical applications now also need to take into account the risk of being attacked from the internet. So we wanted to see how this is done in current devices, and for this we did a large-scale study on embedded firmware. Okay, but before we go into the problems and design of the system, let's first look at some stories where embedded systems were in the media. This is a D-Link home router, and Craig Hefner published a post where he showed that this router has an administrative interface that can be accessed if you set your browser agent string to something like edit by Joel backdoor, which is a nice feature. And it was actually used in D-Link tools because they didn't want to place the user the big burden to type the administrative password in their tools. So they just used this backdoor to change administrative settings. But of course, it's not that cool if anybody can come from the internet with this browser string and then just change their configuration. Especially since a router is your gateway into your home network and is as such supposed to have some security, to provide some security. Well, a second example is a printer. This was work done by André Costin. He looked at firmware of printers and how they process PostScript, and he discovered that actually a lot of the functions of the printer are exposed in the PostScript language. So some of you might not know, but PostScript is a complete programming language. And you can also access some of the internal APIs like peek and poke memory and so on of this printer from PostScript. Also, the PostScript interface is used to update the firmware. And this printer has an administrative password, but most of the features that is exposed via the PostScript interface don't use this password. So it's bad if anybody can print onto your printer and can update the firmware by doing that. The next example is voice over IP systems. This was research done by a group from Columbia University. And they showed that by changing the firmware on Cisco phones, you can, of course, record calls, but this was not interesting enough. They also showed that you can, while the handset is on the hook, listen into the room and thus effectively transforming the telephone into a bug that is inside your office and listening to everything you speak inside the office. So also not something you would want with your own phone at home. And the next example is cars. There have already been several researches that showed that if you can hook into the onboard diagnosis system, which is the access to the CAN bus, the internal network of the controllers in the car, then you have basically access to every function. You can activate the windscreen wipers, but you can also activate the brake, or you can change motor controls. And you can imagine it's pretty bad if somebody decides to use to remote actuate the brake while you're driving on a highway. And okay, this example is more fun, don't take it seriously. But as soon as Amazon announced that they will do a delivery by drone, somebody took a Parrot AR drone, installed a Wi-Fi sniffing toolkit on it, and claims to have a toolkit where you can recruit your own drone swarm by just hacking into the other Wi-Fi and then taking over the control. And of course, I could go on and on and on. There are every week new reports of insecurity of embedded devices. But the problem with this is that each of the analysis that was done there is individual analysis, and there is huge manual effort into in each of these analyses. And if you want to do this at large scale, this is not feasible. But our goal was to do a large scale study, because we assume that if you look at a broader range of firmware, then you will get an understanding of what problems are common across firmwares. So we looked a bit at what approaches. No, stop. So why do we have problems doing a large-scale analysis on firmware? So there is a lot of heterogeneity in embedded systems. First, the hardware platforms are different. It's very different what input, what output you have. Sometimes you don't have text input, output, for example. You just have sensors, remote command, something like this. Also, how hardware appears inside to the firmware is very different. So where it's mapped in address space. Then CPU architectures are vastly different. There is ARM, MIPS, SH4, and a tons of other systems. Operating systems in embedded are much more diverse than in the PC settings. You have VxWorks, QNX, several real-time operating systems, and also library hardware abstraction libraries that are not real operating systems. This on the one hand side, then also the uses of embedded systems are very different. What they want to do with the embedded system, and the requirements they have. So driving a truck is much different from switching your television. And finally, the security goals of embedded devices are very different. The dishwasher of my grandmother doesn't need to have the same security as a PLC in a nuclear power plant. So why does manual analysis not work in this heterogeneous setting? Because for each of these very different systems, we need to find and download firmware. Then once we have obtained the firmware, we need to unpack the firmware and then perform some analysis on it. And then we will discover some bugs maybe. And in most cases, we will probably rediscover bugs that have been discovered in other devices before. So we looked at some previous approaches on that. There was one by Boyanov for analyzing embedded web interfaces. And he used real devices, which of course gives very accurate results. But then on the other hand, it does not scale well, because you need to buy all those devices, which costs money. Then afterwards you need to maintain them. And if, for example, one device gets stuck, you need to reboot it. So a lot of effort, not feasible for our approach. Another approach has been to scan devices on the internet. For example, large-scale testing has been done by Ankui in 2010. But the problem if you do this is you can only scan for already known vulnerabilities, and you have a black box approach. This means if you send an exploit to one device, then it might not respond anymore, but it might not respond anymore because it has crashed, because your packets have been detected by an intrusion detection system and you're blocked now, or maybe the device was just switched off. So you cannot really tell more about what is going on if you do this approach. And also, testing on other people's devices is perceived as ethically questionable. For example, the internet census of 2012, where one guy uploaded code on thousands of embedded systems, then used this code to do a port scan on the complete internet, and afterwards uninstall his code, is probably too intrusive because you cannot just own another device and install code on it. So what is our approach? Well, first we want to collect a large number of firmware images. Then we want to perform a broad but simple static analysis. Simple just because we're 2 persons, and with a manpower of 2 persons, we're not able to do a very sophisticated automated analysis. And then, which is our huge contribution, we want to correlate across firmware to see which vulnerabilities reappear between firmware. The advantages of this approach is that first, compared to what I told before, there is no intrusive online testing, so no people will get upset if we do this. And also, there are no devices involved, so we don't need to maintain a complete device park and buy expensive devices. And also, the static analysis should be scalable, because once you can do analysis on one machine, you can just go to the cloud, you can get thousands of machines, and you just let each machine analyze one firmware. But of course, we didn't solve all the challenges that were there, and many of those remain. So what is difficult about obtaining updates? Here you see the screen of the update screen of 3 popular operating systems, macOS, Windows, Linux. And it's quite well defined, first, what products you have installed on your computer, then how you get updates for those products, and how to get them reliably and from trusted sources, and then how to install those updates. Well, in the embedded world, it looks a bit different. So the usual procedure is that you go to the manufacturer's website. You are not even notified that there is an update available, but you need to check each time yourself. And then you download the update from the website, or it's available on a hidden site, because now manufacturers have realized that this process is quite cumbersome, that you need to check yourself. So sometimes the firmware itself checks if there is an update available and then asks you, do you want to install the update? I think you know this from your TV. But then also the site might be restricted, so firmware updates are only available to authorized users, and the username and password for the website is given somewhere in the manual. Or updates are only available on request. This might be, for example, if you have medical equipment, then is quite rare that you can install the update yourself, but you will have a technician who comes to your facility, installs the update on the device. And finally, firmware might not be updated at all, but just delivered on the device, and that's it. The manufacturer will provide no support whatsoever afterwards. Okay, but this is not the only trouble. Now, the question is, how do you bring the firmware to your device? And again, there are thousands of possibilities. Here are some. For example, for this camera, you put the firmware on the SD card, you choose something in the menu, and it will update the firmware. Or you have this TV box where you need to plug it into the computer, and it will update via USB. You have the printer, which has a service program, which will upload the update over network to the printer. And for example, this hard drive has a CD image. The CD image will boot your computer to DOS. And then inside DOS, the update will be pushed to the hard drive. So you see, it's completely impossible to find a common way for all this firmware. So, okay. The problem was that there was no large-scale firmware dataset available yet. In other disciplines in computer science, this is quite common. Like in multimedia, you have thousands of datasets to test your algorithms with videos or pictures if you want to, but not so for firmware. This is why we collected a subset of the firmware that was available on the internet for download. But still, we didn't catch all the firmwares because, of course, I told you before, some are blocked behind username password access protection. So for this, we have the firmware.ie project, and I will tell a little more about this later. Okay, this was the first challenge, how to obtain the firmware. Then the second challenge is, imagine now you have a bunch of files. For example, you have downloaded files from the manufacturer's FTP server, and you need to say which files are firmware and which files are something else, like drivers, manuals. So for a PDF file, it should be pretty obvious it's not a firmware. If you have a binary file, then it's likely a firmware. If you have an exe file, then it might be something in between. It might be a driver that is self-installing, or it might be a self-extracting archive that then inside contains the firmware. So it's not trivial to just look at the file and say what it is. Let me give you an extreme corner case for this. Here, this is a picture from the service manual of a Xerox printer. And it explains you how to install the firmware. So you will receive the firmware as a PostScript document. And then you're supposed to go to this web page in the printer's user interface. And there you upload the file like any other file you would like to print, and you just press the print button. So it's very hard to say from the outside that this PostScript document is a firmware. And normally you would just sort it out. So the next problem is how to unpack firmware once you have it. And let's just resume the example from before. You take the zip archive that you get from the vendor's website for the printer, and then you start extracting. You have one Windows executable file, and you have a PostScript file. So let's first look into the Windows executable file. And well, automatic analysis doesn't bring us any further, so we look manually, and it turns out to be a printer driver. Well, then this was a dead end. Let's try the PostScript. The PostScript actually contains a ASCII 85 stream inside, which is something similar to base 64. And if you decode this stream, you will get an ELF file. So what is this binary ELF file now? Is it a binary patch that is just to be added to the current printer firmware? Or is it a program that is executed on the printer to change its firmware? Or is it a whole firmware image that is packaged inside? We inspected it manually, and it turned out to be a whole firmware image where the ELF file just describes where the code goes in memory. Okay, but you see it's quite cumbersome. And to automate this process is difficult. So let me summarize. Firmware updates are often packaged as Russian dolls, one in another. And sometimes the result of unpacking is just a binary file. And once you have the binary file, you don't know what to do. So this is the next problem. And there is a solution for that. It's called file carving. And file carving just means that you go at every offset of the file and you try each unpacker that you have at this offset. But of course, you need to have a good heuristics that tells you when to stop. Because if you go to if you try every offset of the file, then if you have a compression format that is quite compact, then it will still start extracting something, which afterwards turns out to be garbage. But you don't know this automatically. And there were existing tools for that. We looked at binwalk, which at that time didn't have a recursive extraction mode yet, which unfortunately meant that we couldn't use it, and BAT, the binary analysis toolkit. The binary analysis toolkit was originally designed to detect GPL violations, but it was quite fit for our purpose because it supports recursive extraction and it supports also file carving. We then extended it with multiple unpackers to unpack strange firmwares. So yeah, as I told you before, if you want to do this brute force carving, then it is quite CPU intensive because you need to go to every offset and you need to try every unpacker, and every unpacker will take some time, some CPU time to figure out that he cannot unpack the file. This takes per firmware almost half an hour to unpack on average. And also, if you have afterwards extracted, we had extracted 26,000 firmwares, if you then have millions of files, then clearly it's impossible to do manual analysis on those files. So even comparison of each file to each other file in each firmware with fuzzy hashes is more and more infeasible the more firmwares you have. How infeasible? You can see here. For the 26,000 that we unpacked, you need 850 days to compare each file to each other, which is still quite feasible if you just put it on a 32-core machine. But then if you do a whole data set of 130K firmwares, then you would need 150 CPU years. This is harder to get. And if you imagine adding more firmwares, since it's quadratic, you will have impossible times. So this is not feasible for very large data sets. This is actually a problem that we didn't solve. Then the next challenge is, imagine you have now downloaded your firmware, you have unpacked it, and you have run the analysis. And you have done the correlation, you have realized that one firmware has a vulnerability and there is a similar firmware that could also have the vulnerability. Then you would need to confirm afterwards if this vulnerability exists in the other firmware. Because just from looking at the static image, you cannot guarantee exploitability. For example, the vulnerability might be in a daemon that is not started inside this firmware because it's not included in the init script. Or it might be in a function that is actually dead code and is never called. So you need to confirm these issues, and this is quite difficult. In most cases, you do this by doing static analysis by hand and doing dynamic analysis on, for example, on a running device. But this does, again, not scale for heterogeneous firmware because you would either need to acquire the device, which is costly, or you would need to have some static approach, but then the firmware are so different that it's difficult. And yeah, if you cannot emulate the firmware, then you really need to buy the device to confirm the issue. So also for this challenge, we don't have a good solution yet. Okay, so far for the challenges that we had. Now let's look at how our system is built. So the first part that you see is the crawler that downloads firmware into our firmware data store. This is a simple database where the firmware is kept. And because not all firmware is available on the web, we also have a web interface where users can submit firmware for analysis. And afterwards, these firmware goes from the data store into our analysis cloud. The analysis cloud consists of a master node. This master node takes the firmware and distributes it to one of the worker nodes. The worker nodes do the actual work, meaning they unpack, they do the static analysis, and they calculate the fuzzy hashes of all the files. Apart from that, there's one special node, the password hash cracker, which takes all the password hashes that were found inside images. So normally in a Linux system, you have, for example, the etc password file, and this file contains password hashes. And because we want to know the real passwords that were used on those devices, we take those password hashes, bring them to the password hash cracker node, which takes first known dictionaries for passwords, but also builds dictionaries from all the strings it finds inside the firmware, and then tries to break those passwords. And this was quite successful too. I will show you afterwards passwords that we broke. So once the analysis of the firmware is complete, the results go into the results database and can be seen on the web interface. And then we have two other systems. One, the data enrichment, which looks at older firmwares and sees if there are new results for those firmwares. For example, when we added the new unpacker. And the correlation engine, which does the correlation between the different firmwares. So I will describe the components a bit more in detail. The first component is the crawler. The crawler is a collection of wget scripts. This is a common tool for downloading. and beautiful soup scripts. And those scripts take as a seed URLs that we have found from searches via FTP indexing engines and custom Google search engines. This is nothing miraculous. It's like you go on Google and you type query strings this firmware and then cite, for example, a well-known manufacturer, or you look for strings that are commonly found inside firmware. By this, we found around 800K of firmware, which amounts to almost 2 terabytes of disk space. So the other source how we get firmware is the web interface. And for those of you who already tried this web interface, because we were already announcing it a bit before, we have put a lot of work inside, and now it should run more or less stable. Please be still kind with us, because we are only 2 people working on this, so we don't have enough manpower to do this next to our PhD. And if you have trouble with any firmware that you submit to the web interface, please just drop us a mail and we're going to look into it. But yeah, I hope it's working a bit better now than before. And it will actually be available starting from tomorrow. Okay, I will describe our data set. We collected around 800K of files. Out of those, we retained 172,000 as probable firmware. And around 30,000 of those we picked for analysis. You can see it's a quite slim fraction of the files that we got initially. But it's easier to just download a lot of files before and then try to find out what is firmware after, instead of doing exact filtering before, because you might miss a lot of files that do not seem like firmware on the first look, but then afterwards are. Okay, out of those 32K, we were able to unpack 26K. And this amounted to 1.7 million files. So it's quite a lot of files for analysis afterwards. On these files, we performed static analysis. The first analysis was for web server configuration. We looked for forgotten credentials inside, for example, SSH keys that were left. We looked for links to code repositories, like subversion repositories. Then a second component would take strings inside the firmware and would look if there are version banners of known software, so that we can get which software package is used and which version of the software package. And then we also looked for keywords for known problems, like telnet, shell, UART, and backdoor. You would be surprised how much you find simply by looking for the word backdoor in firmware. Yeah, there is an example for that afterwards. Yeah, and finally we performed the clustering, which was our work, with the fuzzy hashes and private SSL keys. This I'm going to explain how this works in the following slide. So let's assume we have one firmware here, and we know this firmware is vulnerable from web reports before. And then we see that there are some other firmwares around that are quite similar. And you can see how similar the files inside the firmware are. And afterwards, you can just propagate the vulnerability to a firmware which is very likely the same. And of course, then afterwards, on these two firmwares, you need to do the manual analysis to confirm the results. Another way we use to compare firmware is to look at SSL keys. So for example, we extracted an SSL key or certificate from one firmware that was put into our data store. And we identified that this SSL key is from vendor A. Then what we did is we used so we know vendor A is vulnerable. Then what we did is we used the ZMAP dataset which is a scan of the complete internet for SSL certificates and keys. And we tried to refind keys that we already had in this data set. And in fact, we refound the same certificate from here. And what was surprising was that it belonged to another vendor, vendor B. And those two were not actually related, but we were actually able to confirm that the same vulnerability exists there, which means that they must have common vulnerable components, most likely because there is one OEM manufacturer that provides a platform, and then there are customization vendors that just take this platform, change it a bit, put their own logo and so on, and afterwards redistribute the software, and also redistribute vulnerabilities. So during our work, we were able to file 38 new CVEs, in addition to the CVEs that we refound to older ones. We were able to correlate those 38 CVEs to 140K online devices by looking at the internet census. And it affected around 700 firmware files with at least one vulnerability in our data set. So this is just to have a good laugh, the Chamber of Horrors. We found several images that were built with Linux kernels or BusyBox distributions that were older than 9 years. We found a debug backdoor daemon in some networking and home automation equipment that we are still investigating, so I cannot tell much more about this currently, but look out, there might be a CVE and a report for that soon. And this backdoor allows, at least from local network and maybe also remotely, to take over devices. And we looked for forgotten and backdoor entries and found plenty. I'm going to show you the list on the webpage in a second. Then one highlight was a Linux kernel that is 4 years old, compiled by root on a machine with a public IP accepting SSH connections. This is not what you should do. You should not compile as root. You should not have your build machine publicly available. And this is especially bad since this firmware is from a GPS and aerospace manufacturer. So those guys should know how to secure systems. And then we also discovered vulnerabilities in wireless fireworks systems. And Andre implemented a proof of concept attack for that. If you want interested, then you can check out his paper. It's pretty amazing. So basically, the fireworks systems don't use encryption, and you can just inject packets, you can replay, and so on. So what did we contribute? Well, this is the first large-scale static analysis of firmwares, and also we are the first to provide an experimental set of firmware. We still don't know exactly how we can legally redistribute this firmware to other researchers, but we will figure out. We described the main challenges that were associated with collecting this data set and the analysis. We showed the advantages of performing a large-scale analysis, which is that you can have a global view. And we implemented a framework for doing this analysis. So what we hope that we gain by this is that first, a broader view on firmwares, which is not only beneficial for this report, but is necessary for discoveries of vulnerabilities that are known already and that are just not propagated to other devices. And also the correlation of firmware reveals relationships, like how vulnerabilities propagate between products, like I told you before with the OEM vendor and the rebranding vendor. And it also allows how to see how firmwares evolve, like which bugs get fixed, which bugs reappear. So what you should take away from this session is there are plenty of latent vulnerabilities that have already been discovered but not discovered for this device in firmware. And security is, of course, a trade-off with cost and time to market for those vendors. So they're not that interested in fixing firmware and providing secure devices. So now it's time for the demo. So this is actually our website. No, we're not there yet. So this is the website, and we also need a file. So what you can do is you can take a firmware file. For example, here I took a Wi-Fi SD card file from Transcend. If you have a look, I think it's this one. So if you have a look here, Transcend provides those nice SD cards that also have a Wi-Fi interface. You can plug this SD card in your camera. And then afterwards, this SD card will open a Wi-Fi network, and you can download your files from the web server that is on the SD card without unplugging the SD card from the camera. So we go back to the firmware.re webpage, and we upload this firmware to the web interface. And I really hope that the Wi-Fi doesn't suck so much, but it does. Okay, this is the bad moment. Okay, so normally it should upload now. It's just 4 megabytes. Let's see if... Well, I need to get Wi-Fi back. Sorry. This is not helpful. Is there a fixed network for here? It's not progressing. Yeah, okay, then I'm very sorry. I would like to show you the demo, but without Wi-Fi it doesn't work. So what you should see here is once you upload the file, the website is still a bit complicated. So you can click here on the file once you have uploaded it. And yeah? Yeah, sure. Do you want to tell me the credentials now? It's n. Wait. Okay, so it's Bachi Sweet Spot. How's it called? Okay. Thanks a lot. Okay, it works. Great, thanks. You're saving my life. Yes. Okay, so once the upload is finished, you can click here, and it goes to this page. Then here you can enter your mail address, and then normally you need to fill the captcha. But it says domain not allowed, which doesn't matter so much because well. Okay, but still, so normally you receive the mail. It works now. Before it didn't work, but now it works that you receive the mail. And then you can go here on main, and you can go on reporting information. And then you actually have here a directory tree where you can browse the firmware. And this is a bit too much. But you will see that here you have the initial zip archive that you get from the manufacturer. And then it contains several interesting files like the init.rom.fs, which has actually all the binaries. And if you look into the, well, this is the .dap directory. If you look into the bin directory, you will see that almost all tools are a symbolic link to BusyBox. So the system is actually running on BusyBox. And you also see that there is some references to BOA, which is the web server that the card uses. And if you now look in the .dap directory, you will also see here some files that are quite interesting. Those are the files, the car card upload here. This one is the one that is allowing actual exploitation, I think, of this firmware version of the card. So there you can just browse. You can just browse every directory that is on the card by using directory traversal. Okay, and like this you can explore the whole firmware. Right now it is not possible to download the TAR archive with the extracted firmware. We're also planning on doing this, but give us some time for this. If you want an extracted firmware, just drop us a mail and it should be doable. Yeah, so here you see the mail that you should have gotten. So you have the link to see the report, which is the same page as before, and you have the link to the admin interface. It's quite straightforward. The only difficult thing is to find the link, where to click in the first place when you have uploaded the file.
Does it tell you if there's a vulnerability?
Sorry?
Does it tell you if there is an issue with the firmware?
No. So currently we mostly provide the unpacking. We are putting more and more of an analysis script to tell you this, but we are doing this project next to our PhD, so there is not so much time for that.
You plan to release also information in files correlations. So if I upload my file, I will see also information maybe correlation with other files.
Yes, this is planned. We have not integrated, so this is already done, but we haven't integrated it into the web interface. This should come really soon.
So I might be seeing also other vulnerable firmware.
Yes, yes, this is the goal. So here you can see, if you click here, you can see a list of password hashes that we have extracted and that we have broken. It really doesn't come out well on the beamer, but here, if you look, it's, we are masking the password a bit, but I think this is 1**4. You can guess the other characters. The passwords that are used in these embedded systems are really not that strong. This might be okay on the one hand if it's written in a manual that you should directly change the password, but still several of those passwords are really weird things like telephone numbers, where the telephone number is the number of the company that produced this product. This should not happen. And the same for keys and certificates. Currently, the key hashes here are mostly up so that if somebody finds this key and searches for it, he will drop to our website and then can enter in contact with us to talk about the firmware. But you can see how many firmware had the public key and maybe also a private key for that. Yeah. So back to the slides. Okay, we did this already. So the only thing that is separating you from the beer now is saying thanks. Okay. So thanks to our supervisors who enabled us to do this research, of course to friends and families who are supporting us in the work and the PhD, which is quite difficult. to Black Hat and the sponsors for being able to present here. And of course, thanks to everybody who submits firmware. So the deal with the website is you submit firmware, and of course you're helping us because you're giving us more firmware that we can look at. But on the other hand, what we provide you is this free report, and in the future, hopefully also a correlation with what other firmwares are there, and an archive that you can download with the extracted contents of your firmware. And thank you all for listening to the talk.